To answer the first four problems of the summer packet, we have to be familiar with the order of operations, what we sometimes refer to as PEMDAS. And I know you understand PEMDAS, but I just want to reinforce that the P is representing grouping symbols. So you see parentheses number 4, but if you look at number 3, there are absolute value signs there, and they are grouping symbols as well. Similarly, the E for exponents refers to powers. If we talk about the square root sign, that is something that can be written with a fractional exponent. So there's different ways to represent that E. M and D are multiplying and dividing, but those are two different sides of the same coin. They're inverse operations, and the same thing with adding and subtracting. So when it comes down to multiplying and dividing, we go from left to right, and the same thing with adding and subtracting. So it's fairly straightforward what we do for number 1. And for number 2, there's a couple of steps. We can express that as 6/4. It's better to reduce it if you want to keep it as a fraction. Maybe that's preferred in some situations, or a decimal. Sometimes people don't like to see improper fractions, but both of these are acceptable answers. For the third one, I just want to bring in just two different examples. If you notice, there's almost identical. These are going to lead to different answers, but where we're going to try to isolate the variable, the first thing we're going to try to do is isolate what was grouped here. This 8n plus 10 is within absolute values. Had it been something that was quadratic or something with a square root sign, we would still do the same work to try to bring the -3 to the other side and the 4 to the other side of the equation. And I didn't need to use those parentheses underneath the radical sign, but just to drive the point home a little bit more, when you take the square root of something on your calculator, you'll see the square root sign and then they open the parentheses. That's to just reinforce that that is a grouping symbol. That is essentially a P. It's a double, there's two things going on here. The square root sign, that's an operation unto itself, but also it's a grouping symbol. So it takes a few steps. We want to get the 3 and the 4 to the other side using proper steps. And then if you've heard before that what you do to the left side of the equation, you have to do to the right, what we're doing is, now that we have gotten the 8n plus 10 alone, what we do to the middle to get the n by itself, we have to do to the left and to the right. The function of an absolute value is to take what's on the inside and turn it positive. So it's easy enough to see that 8n plus 10 can equal 14, but it can also equal -14. Sometimes you may have seen this written as two separate equations, solve for both. You can solve simultaneously, since in both situations we're going to have to subtract 10 and divide by 8. You can group them together and get it in one fell swoop. And it's a little bit more appropriate to say that our solutions are -3 and 1/2. Again, if you want to switch that to a decimal, that's fine. And for the fourth one, there's some distributing, some collecting of like terms, and solving. Without the written directions above, we can simply solve to find out that C equals 8. That is the one solution. But the directions ask us to find which values of C would give no solution to the equation. C is the one correct answer, so to answer what's being asked above, we would have to say any value of C not equal to 8 is going to create an untruth, an equation that doesn't make any sense. In interval notation, it would also be true to say that any value from -infinity to 8 and from 8 to infinity would also give us no solution. Now that may seem like that's everything in the universe because we've included 8 in both situations, in both intervals, but those soft parentheses are saying that we could go up to 7.999, etc., or 8.000001, but not the integer 8 itself. In number 6 and number 7, we're asked to do some translating. from English sentences to mathematical sentences, known as equations, or in this situation, inequalities. So I want to make sure that I understand some of my vocabulary. Like quotient means I'm going to divide, and is less than. If I'm going to divide two values, n and 3, the order in which that's mentioned is important, and is less than 5. Here are the other words that you should be familiar with. And when we say more than and greater than or equal to, there's two symbols merged here with the greater and equal sign. There's how we want to express number 7, but I just want to point out in English we say 10 more than y. The 10 is the first number mentioned there, but it's more than y, so we need to have y first. You can be a little bit lazy with the addition and say y plus 10 or 10 plus y, and they'll be equivalent to each other, but put some value in your own mind and say that value minus 10 or 10 minus that value. Do you come to the same answer? With multiplication, can you switch the order? What about division? So you want to be very careful. If you were a little bit lazy and said 10 plus y is greater than or equal to 17 and tried to solve for y, you could still come to the same inequality, but we just want to be very careful. Number 8 is not difficult to do, but I'm going to show 3 methods for a few reasons. One, when I look at number 8, I notice that there's a -3 on both sides, and I might ask the question, why am I going to bother to distribute the -3 onto the x and then ultimately divide by 3? So one method, I might want to just divide right away by -3 so that I get 1 on the left and 1 minus x on the right. But remember, when you multiply or divide by a negative, you have to flip the inequality. Originally, it's a less than or equal to symbol. Now it's greater than or equal to in step 1. In step 2, if I subtract the 1 from both sides, I get 0 is greater than or equal to -x. And I want to know what x equals, or what is x greater than or equal to in this situation because of the inequality. So again, if we need to divide by a negative, we can isolate the x, but we do have to flip the symbol again. So that's one method to get x by itself. I'm going to graph this towards the end. Another possibility is to, in fact, distribute and then add the -3 to both sides, divide by 3, and in this situation, instead of having the double flip in method 1, I flipped in blue and I flipped in green. In number 2's method, I never multiplied or divided by a negative, so I kept the symbol consistently less than or equal to. In method 3, I took what was, both of these are negative expressions, and instead of dealing with the negatives in method 1 by multiplying or dividing by a negative, in method 3, I take the negative on the left and add it to the right, and the negative on the right and add it to the left. So I've flipped the positions and I've kept the inequality symbol the same. Then when I divide by 3, I'm dividing by a +3, which keeps the inequality symbol the same. It leaves me in step 3 with a -x is less than or equal to 0. When I multiply or divide by a -1, I need to switch the inequality symbol to a greater than. And that leads us to another thought, that in methods 1 and 2, my final answer is 0 is less than or equal to x, and in method 3, x is greater than or equal to 0. Those are equivalent statements because in mathematics, you can read from left to right and from right to left. So since we traditionally read from left to right, we would consider that inequality symbol in green up in method 1 as a less than symbol, less than or equal to, and in method 3, the purple is a greater than or equal to symbol because we read from left to right. But your brain can be working in both directions, and I hope that can explain a little bit why it's important to flip the inequality when you multiply or divide by a negative. So those inequality symbols include the equal to, so we fill in the 0, and then the greater than tells us that we're going to be heading out in the positive direction. And as an interval, we would say that all the solutions are from 0 to infinity. But if you notice, this is different than what was on a few slides earlier. This is a bracket with the 0 because 0 is part of the solution, and then we're going off towards infinity. The infinity still has the soft parentheses because we are approaching infinity. We'll never actually get to infinity. Our goal in numbers 9 and 10 is to write the inequality and graph the inequality over on the right, but I thought it might be better if we first wrote the inequalities associated with 9 and 10. For number 9, -1 and 5 are our endpoints, but -1 is part of the solution and 5 is not. So we fill in the 1 and we keep the 5 as an open circle. That's equivalent to, in interval notation, a bracketed -1 and the parenthesis with the 5. Similarly down in 10, from negative infinity all the way up to and including 0 gives us the open parentheses in front of the negative infinity and the bracket with the 0. You can see the similar notation, including 4 and then going off towards infinity with the union symbol in between. When we go to write what are not the solutions, what are the opposites of these things, I want to first show that we're going to come from negative infinity up to -1. Now, -1 was part of the solution in number 9, so we want to have parentheses with the -1 saying that it's not going to be part of it for the second one. And then since our 5 had the soft parentheses, we have a bracketed 5. You can see the first branch of that and the second. Open circles associated with the soft parentheses and the hard brackets associated with the filled in circles. Going in reverse order, we're at 0 and 4 for endpoints of these two rays. So I'm going to have open circles at both of those points. And since it was going to the left and right, I'm going to include what's in the middle for number 10. And to write that is to simply say that we're going from 0 to 4. Notice they were bracketed in both situations over on the left, so there's open parentheses. We're dealing with interval notation right here. So what's happening with regard to parentheses or brackets, I hope you're starting to get the hang of. What I don't want you to do is get caught up in this being 0, 4 and thinking that's somehow x, y, and this is an ordered pair that's going to belong on the coordinate plane. We're just talking about a number line, and we're talking about the two endpoints going in one linear direction. And finally, for this section, for numbers 11 and 12, we need to determine whether the relation, first of all, is a function, and secondly, if it is a function, if it's linear or nonlinear. Here are some examples of functions and non-functions, and the dotted line is checking whether or not these functions pass the vertical line test. If we could shift this dotted line from left to right for the first one, wherever we were to draw the vertical line, would we cross the function once or more than once? Since the answer is at most one time for the first graph there, that's a function. You can see right away that in the second example, it's not a function. If you were to slide it over to the left, it's okay right at the vertex there to touch only once. And if we go over further to the left, it's possible to draw a vertical line and never cross the parabola. It can still be a function, but if it ever crosses twice, then it's not a function. Therefore, our third shape is not either. This follow-up question is, if we do have a function, is it linear? So we're looking for a shape that's perhaps something like this final example, And to do so, we'll have to check our slope, or the rate of change, the rise over the run. If we were to subtract y2 minus y1 over x2 minus x1, is it consistent? So is number 11 a linear function? The first question is it a function? And when I look at my x values and see that we're going from negative 3, 0, 3, 6, 9, each time we have a new ordered pair, we have a different x. That tells us that we're looking like we should have a function. Is it linear? That would depend on whether our slope is consistent. I've checked out a bunch of different situations, and each time when I simplify, I wind up with a slope of negative 1/3. And if I wanted to graph it, here's a illustration from Desmos. I hope you get familiar with this website soon. You can see that it's following a linear path. And for number 12, that relationship is also a function. You should be relatively familiar with this. That's an example of a parabola. It's a quadratic. When it graphs, it's going to look like a parabola. It's in what's known as vertex form. But just as a reminder, in the previous one, number 11, we found out that that was linear, and it could be written in slope-intercept form, y equals mx plus b, where the x is linear, it's to the first power. Whereas number 12 is written in vertex form, but there's a square on the outside. You can also put it in standard form, ax squared plus bx plus c. If we were to graph it, you can see it's the blue parabola that's being graphed in number 12. You can check out over on the left what I typed in. This parent function, x squared, is in red. The negative is going to be a vertical flip over the x-axis, and that +1 is as though it's minus a -1. That's a shift 1 unit to the left. So you weren't asked to graph this, but I just want you to get familiar with what these things look like. And again, if you were to draw vertical lines through either one of these parabolas, would the vertical line test be passed?